Well, now that we've had a brief introduction to the protein thermal shift assay, let's see how someone interested in benefiting from this technology can get started. The first thing a researcher will need is a real-time PCR instrument from Applied Biosystems. Several instruments are supported for this application. The Step 1 and Step 1 Plus, the 7500 and 7500 Fast, the VIA 7, and the QuantStudio. Protein thermal shift reagents can be purchased in one of two forms. For beginners, we strongly recommend the Protein Thermal Shift Starter Kit. In addition to 2,000 reactions worth of buffer and binding dye, this kit includes both a control protein and a control ligand, with which you can practice before attempting the protocol on your own samples. Now, once you feel comfortable, you can immediately move to testing your own proteins using the Protein Thermal Shift Dye Kit, which contains only reaction buffer and fluorescent dye. In terms of the protein samples themselves, please note that ultra purity is almost never required for successful results. This means that you can work with purification fractions to monitor enrichment and stability and thereby avoid cumbersome dialysis steps that many other technologies require. What's more, each reaction well only uses an average of 1 to 2 micrograms of sample protein. We've even seen cases where as little as 50 nanograms of a particular protein produced excellent results. Let's have a quick look at how easy it is to prepare protein thermal shift assay reactions. You'll set up reactions in an optical plate specific to your real-time instrument block. The components break down as follows. 1/2 of the final reaction will consist of either the reaction buffer that ships with the kit or whatever buffer you normally use with your protein, assuming its initial concentration is 2x. So, if these are 20 microliter reactions, you'll add 10 microliters. 1/8 of the volume will be the freshly diluted dye. That's 2.5 microliters per reaction in our case. The remaining 7.5 microliters will consist of some volume of protein being studied, plus, if appropriate, a volume of any component that's being experimentally tested. Water, of course, makes up any volume shortage required to reach 20 microliters. To make life easier and to improve pipetting precision, you should feel free to make cocktail mixes of reagents that are common to a group of wells. For example, let's say that these 48 wells in our reaction plate all need the same amounts of the same 3 components: 10 microliters of buffer, 2.5 microliters of dye, and 3 microliters of protein. We can make a sufficient amount of this mixture for those 48 wells, plus a few extra to be safe, let's say 55 wells. Now, we simply multiply out to get the volumes of each component for the cocktail. We next add these to a microcentrifuge tube, mix thoroughly by pipetting, then add 16.5 microliters of this mix to each well of our reaction plate. We can then add a total of 3.5 microliters of our variable components, say ligand plus water, to complete the reactions. Finally, we seal the plate tightly with an optical grade cover and give the plate a quick spin before loading it into the real-time instrument. To review additional protocol details, including some specific recommendations about what controls should be included in each run, please have a look at the Protein Thermal Shift Studies Guide, available for download as a PDF from the Life Technologies website. This booklet contains part numbers, general experimental guidelines, advice on setting up thermal profiles, and a host of other information that a new or experienced user should find helpful. Now, after reading this document, you'll see how easy it is to set up a run in the real-time instrument software once the reaction plate is sealed and loaded. Well, let's look at a quick example. I'll demonstrate using the Step 1 Plus software, though the process is very similar in all other AB-branded real-time instruments. I double-click the icon to start the software. Once the home page opens, I'll select Advanced Setup. When this page pops up, I can enter an experiment name, make sure my instrument type is selected, indicate that I want to do a melt curve, select the button for Other under Reagent Type, and confirm that the fast ramp speed is chosen. I'll next go over to the left and click Plate Setup. This page and the next allow me to add setup information to the plate, but because we're actually going to do the final analysis in a different software package specifically engineered for thermal shift experiments, I'm not going to invest the time in adding a great deal of detail. All I really have to do on this page is to tell the software that I'm using rocks as my reporter die for target 1 and none for my quencher. I'll next click the Assign Targets and Samples tab. Before doing anything else, I need to indicate that my passive reference isn't the default setting of rocks, since that's actually my reporter die with this application, but instead none. Next, I need to indicate which wells of the plate contain reactions. To do so, I'll simply highlight all wells that contain either samples or controls, and then click the button next to Target 1. And there we are. All wells are labeled sufficiently for data collection. I'll now change the run method to reflect the melt profile for the thermal shift assay, which I can do by going to this menu. First, I'll make sure that the correct reaction volume is entered. 20 microliters is what we want for our run. Next, I'll change the conditions to match my desired melt profile. To do this, I'll highlight this first segment with my mouse, and since I don't need it, click the Delete Selected button. And it's gone. I can now drag my starting temperature down to 25 degrees and nudge the ending temperature up just a bit to 99 degrees Celsius to increase my total range. And that's it. If I plan on using these same conditions over and over, I have the option of saving them to a library of run methods and then recalling that method for future runs. Also, please note that you have a lot of latitude for customizing melt profiles, so if these conditions don't suit your experimental needs, feel free to play around with either the temperature range or the ramp rate. Users of AB real-time instruments even have the option to go all the way down to 4 degrees. That's something other systems don't offer. To get the run going, I'll go to the Run tab. Once here, I need to click Save, give the file a unique name, choose a location for the file, and save. Finally, with the plate in my real-time instrument, I start the run. Once the run completes, we'll need to click the Analyze button. We then click Save, and we close the software. And that's all there is to getting a run completed and ready to be imported into Protein Thermal Shift software. In the next video, we'll see how to use this very unique analysis package to make sense of our final data. And please join me.